talking about acids and bases. Now, a lot of this stuff you guys heard last week when you did the acid and base. Uh-oh. Why do I always do that? I mess myself up. Oh, there we go. Okay. Acids and bases when you did the acid-base lab where you had to do a titration. So a lot of this stuff is going to be familiar. All right, properties of acids. An acid releases hydrogen ions in solution. There's some good formulas for acids, and how do we know those are all formulas of acids? They got the H in front of them, and they got a non-metal something else hooked up to it. Now, some of those are binary, or excuse me, some of those are monoprotic acids. Some of those are diprotic acids. Let's talk about this idea of a proton. All right, let me go to the ladybug here. All right, protons, uh-oh. Yep, maybe I should have done that. All right, let's go. Let's see how savvy I am here. Probably not. So we have, let's see, we have the Bronsted-Lowry definition and the Arrhenius definition. All right, there's two different definitions of acids versus bases. One of them has to do with an acid being hydrogen ion donor, and the base is a hydroxide ion donor. The second definition has to do with an acid being a proton acceptor and a base being proton donor and a base being a proton acceptor. All right, so you need to connect which one of these definitions relates to which one of these terms, and that certainly is in your textbook and in the PowerPoint, but I want to discuss this idea of what they're talking about when they say an acid is a proton donor or a base is a proton acceptor. All right, so we have something like hydrochloric acid, and when we put it in an aqueous solution, it's going to dissociate into hydrogen ions and chloride ions. Now let's talk about this. They call this a hydrogen ion. Is one term you're going to hear used for it. You're going to also hear that this is called a proton. And that's kind of different because we really talked about proton as being subatomic particles before this point in time. And now they're calling something that is a particle that began as an atom a proton. What do they mean? They mean that normal hydrogen, right, has a single proton in the middle, neutron, depending on which form of hydrogen that it has. And how many electrons does a normal hydrogen have spinning around it? One. All right, so it's got one electron. Well, when it splits up, when HCl splits up, the electron that's shared between them goes with the chlorine, and that's why it becomes negatively charged. The hydrogen becomes deficient. It loses that electron altogether. So really all that's left is a proton. So that's why they call an acid a proton donor. It's not really splitting an atom and taking the protons and the electrons and the neutrons and doing stuff with them. What it actually is doing is when it splits up, this thing doesn't have an electron, so it acts like a proton. It is a positively charged particle. So when you see those terms, proton donor, proton acceptor, that's what they're talking about. All right, let's go back to our acids and bases pathway now. So there's the formulas for acids. Now, some of those are monoprotic. Remember, we just talked about a hydrogen ion being the proton. So which one of those acids are the monoprotic? And there's only one that's diprotic. Which one is diprotic? How's that?
HC2H3.
H2SO4, because it's got two hydrogens it can donate. So they call it a diprotic acid. The other ones are monoprotic, meaning they can only give a single proton to an acid-base situation. If you wanted to have what's called an operational definition for an acid, meaning how do you know you have an acid other than the formula? Well, they have a sour taste. Like vinegar, acetic acid is in pickles and salad dressing. That gives it the sour taste. Lactic acid in milk sometimes gives it a little bit of sour taste, and that's what makes the milk go sour. There's all different. Ascorbic acid is vitamin C. I love the taste of vitamin C tablets. It's kind of sour and tangy, you know, those kind of things. And lemons and limes are also acidic. Acids also will dissolve metal to produce hydrogen gas. You guys saw that in single replacement reactions, right? So those are things that acids can do. Acids are also often caustic to organic material. There's some formulas for bases. Now, of those, we have, let's see, two of them that are singular hydroxide donors, and then we have one that can donate up to 2 hydroxides when it dissociates. Same thing with base. You put those in water. They break up like NaOH would break up into sodium ions and hydroxide ions, so they are donating hydroxide ions to the solution. When you pour bleach in your laundry water, you know, if you've got hot water and you pour some bleach and you're going to put the whites in there, have you ever felt the water? Have you ever felt the bleach? It's kind of slippery and slimy. That's a good indicator of a base. Or like soap. Soap is a base. Drain cleaner is a base. All those things feel slippery. They also taste very bitter. When I was teaching at Rio Salado, we had to send students lab kits to do titrations at home, like the titration that you guys did in lab last week. And so what we would have them do is we would take milk of magnesia, which is a really interesting diprotic base, and we have them titrate milk of magnesia with vinegar at home. And so they could do an acid-base titration with milk of magnesia and vinegar. And that's why you take milk of magnesia, is because it's a base and it helps de-acidify your tummy when you have too much acid in your tummy. When you put an acid and a base together, it's called a neutralization reaction. It's just a subcategory of double replacement reactions. Corwin, the author of your textbook, likes to call it its own little category of reactions, neutralization, but most chemists I know call them all a subcategory of double replacement reactions. There's a reaction of nitric acid and sodium hydroxide. Now remember, what are the two products that you always get in an acid-base reaction? Two things you always... Water and a salt. Okay, we got H2O. What's the salt in this reaction up here? Sodium nitrate. Remember, anything that's a metal-non-metal combination is considered a salt by chemists. And so that is the salt and the water that you get in that particular one. And then we got the pH scale, which you guys learned about in lab last week. You have the pH scale goes from 0 to 14. Anything less than 7 is an acid. Anything greater than 7 is a base, also called alkaline. And 7 is supposed to be neutral, where you have equal concentrations of both. All right, so what things are acidic, what things are basic? Your tummy acid is very, very acidic, as you probably already know. The acid that you put in swimming pools is very similar to hydrochloric. In fact, it's probably mostly hydrochloric. Bases are things like milk is a base, ammonia that you put in your water, bleach is a base, drain cleaner is a very, very strong caustic base. So if you have any drain cleaner at home, you don't want to get that on your skin. And you certainly don't want to use drain cleaner in conjunction with any other kind of a cleaner, especially that has bleach in it, because then you start to generate a whole bunch of really bad gases that can choke you as you're cleaning your bathroom. So you don't want to use those things. And make sure you read the label. Don't mix things together. Because if you have a base and you spill a base, you don't want to pour an acid on it. How come? Well, gas is produced, but it's also a very exothermic reaction, right? So you don't want that heating up and causing things like that. And a buffer is something that simply just helps to maintain the pH. It helps a solution to resist acid and base additions, and it sort of, it's like a mediating force. And we don't talk a lot about buffers in here, but if you're taking 152, we'd spend an entire chapter just on buffer things. All right, there we go. There's our definition. Arrhenius acid produces hydrogen ions, and Arrhenius said that a base produces hydroxide ions. So there's the definition for Arrhenius acids and bases. Arrhenius also said that the strength of an acid has nothing to do with the concentration. So let's give an illustration there that I think is going to be super helpful. All right, we're talking about strong acids. So strength of an acid or a base has nothing to do with the concentration. All right, I want you to put this in your brain. So something that's a strong acid or a strong base has nothing to do with how much it is concentrated. All right, strong acid. What happens with the strong acid is they dissociate completely. Meaning every single bit of acid that you put into water completely breaks up into its component parts. All right, so we have 100% dissociation in strong acids. So hydrochloric, nitric are both strong acids. That means every single bit of this that I put into a solution, it's going to break up into those things. That's what a strong acid is. Now a weak acid, we're only going to mention it in this class, but when you get to Chem 152, you spend, once again, an entire chapter talking about weak acids. And weak acids only dissociate partially. Usually less than 5%, right? So if we've got 100% of these dissociated in a strong acid, in a weak acid, less than 5%. A good weak acid is acetic acid, vinegar. And we use this kind of an arrow. This is called an equilibrium arrow. This kind of an arrow here is called a completion arrow. In a completion arrow, what that implies is that the reaction is going to completion. That once you put this stuff and you make an aqueous solution out of it, it's going to break up into all these things. This kind of an arrow is called an equilibrium arrow. That means that some stuff is going to go in this direction, but that some stuff is also going to go in the reverse direction. And you have an equilibrium set up between what's here and what's here, and you're going to have all three of these things in your solution. So in a strong acid versus a weak acid solution, we could have 3 molar, right? Be the same concentration. Say we had 200 mils, same volume, right? Same concentration, same volume. In a strong acid, we're only going to have these things in there. In a weak acid, you're going to have hydrogen ions, you're going to have the acetate polyatomic ions, and you're going to have the undissociated particle that started with. So you're going to have mostly those, a few of those, and a few of those. In a strong acid, you're only going to have these kind of things here. All right? So strength of an acid is nothing to do with the concentration. The strength of an acid has to do with how much they dissociate it. Now, if you know the 7 strong acids, is it 7 or 9? 7. I think you're right. It is 7. Yes?
So if it has nothing to do with concentration, why is it that like the weak acids still have like whole molecules for actually in the liquid?
Because it's hard to dissociate them for reasons of attraction of the individual ions to each other. These, although they have an attraction for each other, the attraction that water has is greater than the attraction they have for each other, so it pulls them apart. Here, these have an attraction for each other, but the attraction that they have is not as strong as the attraction here, and so water can't break them up as much. So it just has to do. So the 7 strong acids are, let's see if I can remember them all, HCl. So if you know all the strong acids, everything else is weak. HCl, sulfuric, nitric. Let me think. No, acetic is a weak one. There's 4 more. There's, the funky ones, the chromic. There's 4 more. I don't know what they are. You should look them up. But if you know the 7 strong acids, everything else is weak. Same thing with strong bases. Now, strong bases are easy to remember. Strong bases, something like sodium hydroxide. If it's an aqueous solution, it's going to dissociate completely into its component ions. If you have a weak base, something like, let's see, beryllium hydroxide, remember which one was weak, it's going to have equilibrium error because you're only going to have a few of those things breaking up. All right? So strong bases. So to know the strong bases, it is the strong bases are the hydroxides of all alkali metals. If we look at the periodic table, the shadow box outline of the periodic table, where are the alkali metals? That first column, right? So the hydroxides of all the alkali metals, things like lithium hydroxide or sodium hydroxide or potassium hydroxide, right? Those are all strong bases. So we have 1, 2, 3, 4, 5, 6. So there's 6 there, 6 strong bases. The other 3 are the last 3, rubidium, cesium, and francium hydroxide. And then the heavier of the alkali earth metals, meaning things like calcium, strontium, and barium, right? So if we had calcium hydroxide is a strong base. All right, so these are the ones down here. So not the wimpy ones. Beryllium and magnesium, no, but the heavier of the alkali earth metals, which are that group right there. So if you know the strong acids and the strong bases, everything else is weak, and it has to do with the dissociation. So the concentration between strong and weak acids can be the same, and the concentration just has to do with how much solute you put into a particular volume of solvent, right? Strength has to do with the degree of dissociation. Here's a good way to remember it. I love lemonade. I finally got my mom to try Chick-fil-A. And the one thing she likes about Chick-fil-A is the one thing I like about Chick-fil-A, which is their amazing lemonade. And they make it with just lemons, sugar, and water. It's the most delicious lemonade you could ever have. I like my lemonade very concentrated. Okay? I don't like wimpy, dilute lemonade. So now some people might say, you like your lemonade strong? No. Because lemonade is made with ascorbic acid, which is a very weak acid. So you can never have strong lemonade. You can only have concentrated lemonade, right? All right, so dorky chemistry jokes. Help you remember these things, that concentration has nothing to do with the strength of an acid or a base. All right. Yes, oh, you had your hand, don't have your hand up, you're just stretching. All right, so strengths of acids, strengths of bases, strong and weak. There we go. There's some of the strong ones. Hydrochloric, nitric, sulfuric, and then there's 4 weak ones. I don't remember what the other 4 strong ones are. I'm sure if you looked them up on the internet, it would tell you. And there's an animation, but I don't dare go out through that because I don't mess up my whole display again. So you guys should look at the animation of the strong and the weak acids. I think it's kind of humorous. All right, so there's how they break up. Strong acid, weak acid. Oh, there's another vocabulary term. Now we've got something else to pay attention to because they're going to be asking you what these things are, and you got to know the term. So we have hydrogen ions, right? This thing is called hydrogen ion. This thing is a hydroxide ion. And this thing is a hydronium ion. All right, so some really interesting terms that are just a little bit together. And this all relates to what we call the AUTO, auto ionization of water. I'm going to use your Kirkland bottles here to give you eggs. All right. These are the worst bottles you can possibly drink water from. These are the ones that you're actually drinking a bit of plastic. So if they crinkle like this, they're really bad. You're drinking plastic, my dear. Okay. A better bet is to buy glass or get the heavy plastic bottle like that. That's much better. Those or the Smart Water or Gatorade bottles that are really heavy duty plastic. They're not as soluble as this stuff. And then I have a friend who buys cases of this. My best friend buys cases of this from Costco. And I went with her to Costco one time. I go, what in the world are you doing with all that bottled water? She goes, well, I have a family of 4. They're all drinking it. I go, get yourself an RO system, save yourself a lot of money, and stop killing your family. She goes, what are you talking about, Laurel? I go, every time you drink some of this, you're drinking a little bit of plastic because it is soluble. These crinkly bottles, the plastic is soluble, and you're drinking that. And I'm telling you, in 20 years, 30 years, your generation that has drunk the majority of your water out of these crappy plastic bottles, they're going to find some funky cancer they're going to attribute to long-term ingestion of plastic from these plastic water bottles. My best friend, I told her about all this, and I'm giving her a hard time. You know what she tells me? She goes, I read about that, Lorelei. She says, you only have to worry if you leave it out in your car for a while and it gets hot. She goes, if I leave it out in my car for a while, I just throw it away. I go, do you think the manufacturers are that responsible? That they're going to keep it cool in shipping it from one place to another? What do you pay for these things, like 11 cents a bottle? You think they're going to keep it cool and worry about the fact that you're ingesting plastic? Probably not. So that's a really good way to drink your water, is in a reusable container like that. Hopefully it's not aluminum.
I honestly don't know my dad.
Okay. Aluminum also, they have found if you drink from aluminum containers or cook with aluminum pots and pans, specifically if you're like me and I love cherry Coke out of aluminum containers, that acidic Coke actually helps to dissolve more of the aluminum, and it helps onset of early Alzheimer's ingesting aluminum. So there's all kinds of things. Anyways, let's get back to ionization of water. I know, that's right. Okay, so auto-ionization of water. This is happening right now in your water bottles that you are enjoying your water out of. Enjoying your water that has lots of plastic in it out of there. What happens is, keep in mind that's an equilibrium arrow, right? Equilibrium arrow is going from, that's called the auto-ionization of water. So you need to know the things that you have. This stuff also sometimes hooks up with this stuff to make this. And that's where this hydronium ion comes in, all right? So sometimes when water auto-ionizes itself, it hooks up with another water molecule and makes a hydronium ion. And this actually happens much more likely. They used to say that this was what makes a substance acidic, but in reality, when you actually release those hydrogen ions in solution, they hook up with the water really quickly, and they make hydronium ions. So they used to say pH is the negative logarithm of the hydrogen ion concentration. That was the old school chemists. New school chemists now say pH is the negative logarithm of the hydronium ion concentration, because this auto-ionization of water makes hydrogen ions that hook up with water molecules and make hydronium ions rather than hydrogen ions staying in water for any period of time. All right, so now none of you are going to drink plastic water anymore, right? That would make me happy. All right, so neutralization reactions. Let's talk about some calculations. You guys can do all that kind of predictions. There's more definitions that you should definitely make sure that you look at. Amphiprotic. Amphiprotic means something that can be an acid or a base. And then indicators. Which one of those indicators did you guys use last week in your acid-base lab? Phenolphthalein, right? And you knew that because I made you say it 3 times. Yeah. And this was all, remember, it was an acidic solution. Remember, it turned bright pink. Remember, I said you wanted to get the really pale pink and not that fuchsia pink. That was the fun one. There's other different indicators for different substances and different pH changes that you're looking at. And then we get to titrations. All right, so let's talk about the calculations. Here we go. Take out your calculators. I'll wake everybody up. They can do some calculations. All right, so let's look at our and we've got 37 mils of acetic acid. Anyway. Alright, so if we look at this problem, I just took some quick notes down so that we could do the problem. This is very much like the calculation that you did last week in lab, right? We had acetic acid, which is vinegar. You titrate it with sodium hydroxide. This is the exact reaction, right? Now what did you get when you put these things together? Good old H2O, and what else? And the sodium acetate. All right, so once again, I like to draw pictures. It says we got 37.55 mils of the NaOH. So I always put it up here so I know what values are going with which stuff. So 37.55 mils of that, and the concentration of it is 0.223 molar. All right? And it says we're starting with a 10 mil sample of acid. Boy, that sounds really familiar, doesn't it? Right? Didn't you take a 10 mil aliquot of acid, you put it, and you started titrating? I think our sodium hydroxide was 0.5 molar, so it's a little bit different. All right, so we want to know what's the concentration. So now those square brackets means concentration of. That's the chemist. That's what the square brackets mean. So whenever you see something like this, what's the concentration of the NaOH, right? They want to know what's the concentration. So in this case, they want to know the concentration of the acid. All right, well, what do we know about this? And we can do it two ways. Since this is a one-to-one, we can use MAVA equals MBVB. But let's do some stoichiometry instead. What do I have right there that can tell me something about how many pieces of NaOH do I have? What's this number right here?
The volume.
That's the volume.
Molarity, so you can find.
So if this is our definition, molarity is moles per liter. I have the concentration, right? I have the volume, so what can I find? The moles. So moles would be equal to what? Molarity times the volume. So let's just plug those numbers in. We'll do it down here so I got some more space. So we're going to take our molarity, in this case 0.223 molar, and we're going to multiply it by our volume. But what do I have to do that volume first so that it corresponds to our molarity units, which are moles per liter? I got to change it to what? To liters. All right, so I'm going to take my 37.55 mils, go from mils to liters. So in essence, I'm moving the decimal point 3 places to the left. 1, 2, 3. 0.03755 liters. All right. Somebody with a calculator. What's 0.223 times 0.03755? 0.008. That's it?
Well, it is a lot.
Let me have some more numbers. 8.
37.
One more. 3. Okay. And that would be, what are my units here? Moles of what?
NaOH.
NaOH. Super important. So you know what you're doing, and what you have is to write units and substance on every numerical value. All right. Well, if we've got that many NaOH, and I say, oh, I've got 0.008373 moles of NaOH, and I want to relate that to moles of acetic acid. What's the coefficient that I would need to use there? Looks like 1-to-1 to me, right? Moles of NaOH to moles of acetic acid. Then, oh, that's all I need to do. So now I have 0.008373 moles of acetic acid, right?
Mhm.
Sure I do, because it's a one-to-one relationship, right? If I got that many moles of this stuff, I'm going to have that many moles of that stuff, because remember when you're neutralizing something, this is an acid, this is a base. We add them together till we get to the neutralization point, right? When the concentrations, the moles of acid has to equal moles of base, so the number of moles is the same. So here I've got that many moles of acid, but that's not my concentration. How can I figure out my concentration? Well, let's write this number down because I'm running out of paper here. Moles of the acetic. Now, I need concentration of the acetic, but what else do I have that I can use to get to concentration? The 10 mils, right? Because I have moles, and how do I get that? How do I get concentration out of that? Moles over liters, so I just take my liters, and what do I got to do to 10 milliliters? I got to change it to liters, right? So 0.0100 liters. Something with a calculator. I'm not good at dividing fractions. It's probably something like 0.8 maybe.
Yeah, you just take off the 2 zeros.
So it's 0.8373. Okay, what are my units here? Molarity of what substance? Acetic acid. Now let's look at sig figs. Well, it looks like I'm limited probably to 3, I would bet, based on there's 3 there, 4 and 3. So what should I change this value to? 837 molar. So you guys could have used the MAV equals MBVB problem way to solve that, but that's only if it's 1-to-1. I think I have a problem here that's not 1-to-1. There's the, here we go. All right, here's one that is not monoprotic acid. Here's one that have a diprotic acid. All right, so we got sulfuric acid and some sodium hydroxide coming together, neutralization reaction, and it looks like we got 10 mils of the sulfuric, and the concentration of the sulfuric is 0.555 molar, and our concentration of the NaOH is 0.233 molar, and they want to know how many milliliters we need to do that titration. All right. Well, took some notes here. Just got the ladybug. All right, well, before we can go anywhere, we got to balance this to figure out how many pieces we need to go on each side of the equation. Well, when I put these things together, since it's an acid base, what are the 2 things I'm always going to get? Water and salt. So we got some water there. And what's my salt going to be? Some sodium sulfate. All right, here's where we have to go back 8 weeks and look at nomenclature. Thank you. You got to have 2 sodium. How come?
Because the charge on the
Sulfate's -2 and sodium's only -1. All right, now we need to balance this beast. How do we balance this? I think we need that because we got 2 there. Then I think we probably need a 2 in front of the H2O. No? What do we need? 2 H's, 2 H's, there's 4. Yeah, we do. So then we got 4 H's there. We got 4 O's, 5 6 O's, 4 5 6 O's. All right, so now we're good. All right, I've written down the problem, made a picture, 10 mils of that. There's the concentration. They want to know how many mils. And there's my concentration of my sodium hydroxide. Well, right off the bat, what can I get out of this? What should I use? What should I approach first?
you could get the moles.
Here's my, I'm going to give you a hint. And if you remember nothing else from this entire semester of chemistry, remember this. If you come to a chemistry problem, whether it's on the MCAT, the GMAT, the GRE, or the final exam for this class, and you look at that problem and you go, yep, that's a chemistry problem, and your blood pressure starts to go up, and your hands get a little sweaty, and you start ringing in the ears, 2 things you should do. Number 1, convert something to moles. Number 2, look at the balanced equation. Every single chemistry problem you do will have those at some point in the problem. So if you have no idea where to start, just remember that 2-step problem-solving method. Convert something you got to moles, and then look at the balanced equation, all right? Easy peasy way to remember how to solve any chemistry problem. And when you're taking the GRE or the MCAT, and that actually helps you find the answer, you can send me a little prayer and say, thanks, Dr. W, for sending me that. All right, so what can I get moles out of here? Looks like that, right? Moles is going to be equal to what? Liters, so we got to go 1, 2, 3. So 0.0100 liters times my concentration. Now I think what that means is going to be 0.0555 or 2 O's. Okay, thank you. What are my units here? Moles of sulfuric acid. Units and substance are going to make your life so much easier, I promise. So let's start with that. 0.00555 moles of sulfuric. Now what can I get with moles of sulfuric? Remember, to convert something to moles, I'm going to look at the balanced equation. So I got to relate moles of sulfuric to what?
Sodium hydroxide.
Moles of sodium hydroxide. Very good. See, you guys got, like I said, if you remember nothing else, nothing from this class, convert something to moles and look at the balanced equation. All right, what's the coefficients that go here? 2 to 1. So that means that would be, oh boy, 0.01 something? 111. Thank you. And what are my units in substance here? Moles of sodium hydroxide. All right, we're getting closer. Is that my answer? No. Not quite. So if I got 0.0111 moles of NaOH, what am I going to do with that? So we got a little bit of different algebra going on here. So if I take our basic formula, and I know that that's true, right? If I do a little algebra, those two derivations are true. I want to find out volume. So what's volume algebraically going to be equal to? Moles over molarity. And there's the hard part. So if you don't know how to do that algebraically, just take that formula and put it on your 3x5 card. So I got moles. What am I going to divide it by to get the liters? My molarity. Okay, somebody with a calculator, what is that number?
0.048.
Okay, and they want a milliliter, so what should I do with this decimal? 3. 1, 2, 3, so it's 48 milliliters. Aren't these fun?
Yeah.
I know you guys love stoichiometry, because what, like half the class got an A or B, for heaven's sake, so you guys should all be good with this. Is that the number we got? 49.8? I think it is. Something like that.
You got 48.
Pretty close. Pretty close. All right, here's where you're making a standard solution. And now they're starting with something that is a mass rather than volumes, but it's all the same kind of mathematical calculation. And now they say they want to know, they got, so we got hydrochloric acid, HCl, aqueous solution. We also have some sodium carbonate, an aqueous solution. Oh, but that's not an acid base. Huh, interesting. All right, well, we'll still do it. 2HCl plus sodium carbonate gives us 2 NaCl's. Oh, I see, it's a decomposition. All right, and CO2. All right, so the molarity of hydrochloric acid, so we want to know the molarity. If 25.5 mils are required to neutralize 0.375 grams of Na2CO3. All right, I got the picture. Summary of the problem. Here we go. Once again, universal method for solving all chemistry problems. If you have no idea where to start, what are you going to do? You're going to convert something to moles. What could I get moles out of here? Grams. All right. Right off the bat, let's just do that to moles. 0.375 grams of sodium carbonate. And I want to go from grams of this junk to moles of sodium carbonate. Let's see, sodium is 23 each, so we got 2 of those. Carbon is 12, oxygen is 16 each. 6, 12, 18, 19, 20, 6, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 106 grams per mole. Somebody with a calculator. What's 0.375 divided by 106? Hopefully I got that molar mass right. What's our number? 0.375 divided by 106.
0.0035.
And what are my units here? Moles of the Na2CO3. All right, so if we got 0.0035 moles of Na2CO3, what do I want to use to figure something else out about that? I want to now, I convert something to moles, what's the next step? Look at the balanced equation, look for mole-to-mole ratios, right? So we're going to go from moles of Na2CO3 to what?
HCl.
Moles of HCl. What's the relationship there? 2 to 1. All right. So that's probably 0.070. Is that right? Times 2? Oh, there's 2 zeros?
Yeah.
I told you I'm not good at this. All right. Moles of HCl. Is that my answer? No. What do I got to do? Well, I got to go. So that's moles. I want molarity. So if I want molarity is moles per liter, what should I do? Divide my moles by liters of the junk that I needed. Change this to liters, 0.02550 liters. And what's my molarity?
0.277.
Molarity of HCl. See, you guys can do these really complex problems now. Not a problem. Convert something to moles. Look at the balanced equation. The rest of this semester, the rest of 151 and a good portion of 152 will get you through in those 2 pieces of problem solving advice. Convert something to moles and look at the balanced equation. All right, that's it. I posted the homework, and it's going to be also due on Wednesday, so you'll have 2 homeworks due Wednesday. You have a quiz on acids and bases on Wednesday.